Okay, so here we go. We're going to start. These are objects at equilibrium. We just did a demo in the lab, and what we saw was a hanging mass, and we understood that the object was not accelerating, and so therefore the forces must be balanced. So we're going to start there. An object with balanced forces acting on it is said to be in equilibrium. Okay, so for example, you have some object, maybe 20 newtons down, 20 newtons up, 50 newtons right, and 50 newtons left. You can see that while the forces might be different, 20 newtons up and 50 newtons right, the object is still in equilibrium because the forces are balanced. And keep in mind that this object, according to Newton's first law, it may be at rest or in motion. If it was in motion, it would be moving at a constant velocity, and if it's at rest, obviously it's at rest. So if it's in motion, you might as well just put a little bracket there to remind yourself, constant velocity. And when you're doing questions on exams and worksheets, often if they write constant velocity, then it's a tip-off to you that the forces are balanced. And that's one of those things, like when you're working on worksheets or exams, it unlocks the problem. You have to understand balanced force, and then you go from there. So what we were working with in the lab there, or examining, was a situation where they call it static equilibrium. And in physics, when they use the word static, what they mean is stationary. Good. So static will be stationary. And then equilibrium, obviously the forces are balanced. Okay, so then we're going to draw the picture that we had in the lab. We basically just had a couple.
Please excuse the interruption. All football players, please go to the locker room. All football players, go to the locker room.
We just had a couple T-stands here, and what we had was a hanging mass at a different angle, at different angles. So you just had a couple strings attached at a knot, and then hanging down off the knot was a mass. And then what we're going to do is we're going to draw a free body diagram at the point indicated here. So when in equilibrium, the net force acting on the object, and when I say object, I mean that knot right there, should be 0 newtons. The net force is 0 newtons. So that means when you add up all the forces, what should you get? So in other words, add all vectors, in their components, right? Do x's together, y's together, add all vectors, and you should get 0. Okay, so this was the picture of the lab that we had. Now what I did was, once I had the picture taken, I printed it out obviously, and I tried my best to draw a horizontal line at this knot, and then I used my protractor. And that's what I kind of had planned for today, but due to time constraints and such, I'm probably just going to give this to you. Okay? So what I did, I put a protractor right at the knot, and I went from there. So looking at the two pictures of the scales, let me get those up for you. And I had them organized left and right, and I'll give them to you in the notes in a second. But I just stared at this. So roughly I had, looks like 8 newtons here. It's the bottom of the plunger, so roughly 8. And you know, it's not the most accurate tool. And then this one here was roughly 6, roughly 6. Okay, so on your paper, I'll help you connect it to what's on my screen, and we'll go from there. Okay, you got a blank page. Okay, so what you're going to do is you're going to just sketch out the situation. And that's the point we're interested in. And you can do this right on the paper. Sketch it right on the paper. Okay, and what I used was a protractor that was decently accurate, and I got 44 degrees here. And I got 36 degrees here on the paper. And I called this one tension left, and I called this one tension right, and of course the weight of the masses due to gravity there. The tension on the left string I had roughly 8 newtons, and the tension on the right string I had roughly 6 newtons. And of course those are just approximations on not a very accurate device. Okay, so where do we go from for here? Where we go once we have a free body diagram is always what? Once we have the FBD, what do? Yeah, you can find the components, of course. But it always goes like this, free body diagram, and then first comes the marriage, then comes the baby. Here comes the free body diagram, next comes the FNet, you guys. Always free body diagram and then FNet. Okay? So, and like Eldrin said, you need to do FNet in the X and FNet in the Y. Okay, so let's start off FNet in the X. Alright, which forces are acting in the horizontal direction? What do you have? Sorry? Tension left in the X, and also tension right in the X. Is it okay how I wrote that? Or is one of them negative? One of them's negative? Which one? The one on the left or one on the right? It depends on what you want, right? So let's just do what we always do. Left is negative and right is positive. So let's clean that up a bit, make it more to what we're used to. So let's put the positive one first. So TRX minus TLX. And what did we say in the lab? That the net forces have to be 0. What does it say in the notes for an object at equilibrium? The net force is 0. So like this object is not accelerating. So that tells us some key information. It tells us that MA is 0, i.e. A is 0. So this left side is 0. So then what does that tell you about the tension right and the tension left? Yeah, equal in magnitude, yeah. So tension in the left equals tension in the right. Okay, and how do we solve for those? Let's use our data. What was our tension left? Our tension left was 8 newtons. So 8, and then what do we multiply by to get the x component? The x component? Cosine of 44. Okay, and on the right side, it should be 6 newtons times the cosine of 36. So go ahead, type those in the calculator and see if those are the same. Do you expect them to be the same? As an experimenter, were our devices perfect? Was my measuring with the protractor perfect? So what do you expect? A little bit off. We should expect some experimental error. So on the left, what did you guys get? 5.7547, and on the right you get 4.8541. Okay, so it didn't line up to our theoretical model. Are we going to break down and cry, or or are we going to understand why? So you can go ahead and calculate the error on that if you like. You know, it should be equal. It's off by a little bit. You know, I calculated, roughly 15% error. Okay, and we have our tension x and our tension. Okay, equal and opposite. Okay, so question. To be more equal? The biggest error I think is in the scale, because when I look at that plunger, I just approximate to 8 newtons. It could be, that scale is not very accurate.
Plus the springs can slide.
Yeah, those springs might be warped. Yeah, exactly. Yeah, so there's a lot of things going on for sure. Okay, so now let's do F net in the Y. And F net in the Y. What's happening there? What are all the forces happening in the Y component? What do we have? Which ones are acting positive? So tension left Y and tension right Y. And is there any other Y forces? There's Fg. And which way does Fg act? Down. So let's make that negative Fg. And we know that the net force is 0 in the Y direction. So you can see clearly that in order for this object to be hung at equilibrium, that the two components of the tension in the Y direction, when added up, have to match the force due to gravity. If this doesn't match, it's going to accelerate down towards the ground until something does match it. So you can see that the Y components of the tension have to sum to add up to the force due to gravity. So the force due to gravity, it was 0.95 kilograms, or 950 grams. Multiply that by 9.81. And again, there's also some error here, because it might not be exactly 9.81 where we are on the globe at Edmonton, Alberta right now. It might not be exactly 9.81. So there's also some error there. And then the tension left in the Y, how are we going to calculate that? Instead of using cos, we're just going to use, good, so 8 sine 44 plus 6 sine 36. Okay? And then after some calculation, what do you get? So this one was actually way closer, which I found interesting. when I did this. So I'm just trying to model sort of the scientific process here for you guys. Now see if you can do the error calculations on your own. I got 15% for the first one and 3% for the second one. Like if they're supposed to be equal, subtract the difference and divide it by one of them. Just pick one of them to be the one you want. Okay, so what we're going to do is we're going to try one in the workbook, and then I'll assign the rest for homework. Any questions so far? Lots of key ideas going on. Free body diagrams, sum of force vectors, objects not accelerating is equal to 0. Lots of stuff going on. So you really got to practice your physics. Please and thank you. Let's go to the workbook. I'll just subtract the two numbers. That's how much they're off by. And then just divide by the one that you think it should be. Like, yeah. Not a big deal. Like, yeah. It's going to be, the first one had small error and the other one had a little larger error. You just tell by how much they're off. Yeah. Okay, let's jump into the workbook. The hanging masses. Just trying to find the page for you guys. Okay, so on page 117, okay, page 117. Okay, these two questions will be for homework. Okay. Make note of this, please. We're moving on. Page 117, these two questions are for homework. The nice thing about these two questions is you have the appendix there to guide you. Okay? I'm looking for a question that doesn't have right angles. Damn. 30, 60, 90? Maybe in the extension. That's where I'm headed. Okay. This one here. This on page 151 and number 7. Okay. Okay, this is the one that I'm going to demo for you. So you guys ready? Okay. Do we have time? So what we're going to do, because these angles are not made with the x-axis, well, they kind of are. But I would still analyze this point here and draw the free body diagram from this point. Okay? Now with that horizontal being drawn across, do you guys agree that this is also 20 degrees? And that this is also 60 degrees? Okay, good. So what we can do is we can analyze these tensions. I don't think we're going to have time in 6 minutes. Go really fast? Okay, so break these down into their two components. T1x and T2x. And here we have T2y and T1y. And it'll be very similar to what we had over on the other page, but it's going to be a little bit longer because you probably need a system of equations. Okay, so F net x is T2x minus T1x, because one is headed to the right and the other is headed to the left. And because F net is 0, we know that those two forces have to be balanced, equal and opposite in direction. And we don't know the tensions, and that's what makes this challenging. Like on the lab that I just demonstrated, you knew the tensions through your experimental data, and it was quite straightforward. You just plug in and play. When you don't know the tensions, you're going to have some systems of equations. Okay? So this first one, T1x, is going to be tension 1 cosine 20, and tension 2 is going to be, or tension 2x is going to be tension 2 times cosine of 60. And that's your first set of information for what looks like a system of equations. Now we jump into F net y. Pardon me? You're going to have to probably find some more room. Yeah? Oh, and you want to draw a tail to tip diagram? Yeah, you can do that. It's just not going to be right angled, so you could use like sine law, cosine law. Yeah. Okay, so F net y is going to be tension 1 in the y plus tension 2 in the y minus Fg. Good. And we know that it's balanced, so F net is 0. So T1y plus T2y minus Fg equals 0. So moving Fg to the other side, and we have tension 1 sine 20 plus tension 2 sine 60. Now, the left-hand side of that equation is just Fg, so 10 kilograms times 9.81, you have 98.1 equals T1 sine 20 plus T2 sine 60. Now, as far as solving this system of equations, you do now have all that you need to solve it, and I'm going to leave it as exercise for you guys. But what do you see? Left side, how many unknowns? And right side, how many unknowns? 2. So what I would do is I would just divide cos 20 on this side, put it over here, cos 60 divided by cos 20 times T2, and then you have an expression for T1. You can substitute that whole right side into T1 over here, and you'll solve. Use a substitution. Okay, so I'll leave that one as exercise, and the sub tomorrow will finish this question off for you guys. Mr. McCracken.